Imagine being asked to build a structure the length of a football field, not on land, but 400 kilometers above Earth. No ground, no scaffolding. This is the construction site of the International Space Station. At this altitude, the ISS moves at about 28,000 kilometers per hour, circling Earth every 90 minutes. Day and night alternate every 45 minutes, again and again. Those rapid transitions force the ISS to heat and cool constantly. Its structure swings from roughly plus 120 degrees Celsius to minus 160 in less than an hour. There is no foundation in orbit. The ISS cannot rest on soil, rock, or concrete. Instead, it remains in continuous free fall, moving forward fast enough to keep missing the Earth beneath it. This condition is often called microgravity, but gravity has not disappeared. The ISS and everything inside it are simply falling together, creating the sensation of weightlessness inside a moving system. Yet even here, space is not completely empty. A thin trace of Earth's atmosphere still reaches this altitude, brushing against the ISS and slowly stealing its orbital energy. That drag is small, almost invisible, but it never stops. Without correction, the ISS would gradually lose altitude and eventually re-enter the atmosphere. So even before we talk about construction, we must understand this. The ISS is not floating in a calm vacuum. It is moving, adjusting, and resisting its environment every single day. Beyond atmospheric drag, the station must also endure radiation from the sun and constant risk from micrometeoroids traveling faster than bullets. There is no protective sky above it. This is the environment where the International Space Station was assembled piece by piece. Not in a factory hall, but in orbit, where every connection had to work the first time. If this was the environment, the International Space Station could never be launched as one complete structure. No rocket could lift something that large in a single piece. So it began as separate modules, launched one by one. The first module, called Zarya, was launched in 1998. It provided initial power, propulsion, and basic control, acting as the temporary backbone of what would eventually become the ISS. Weeks later, Unity was attached to Zarya. This connecting node allowed future modules to dock from multiple directions, turning two isolated components into the beginning of a growing structure. From the start, the ISS was designed as a modular system. Each segment had to function independently at first, yet be capable of becoming part of a much larger integrated station. The size of each module was limited by the diameter of the rockets that carried them. That constraint shaped the station's design long before it ever reached orbit. That is why most ISS modules are cylindrical. A curved surface distributes internal pressure more evenly, making it structurally efficient in a vacuum environment. Inside the ISS, the air pressure is kept close to 1 atmosphere, similar to conditions on Earth. Outside, there is almost nothing. The station's walls separate life from vacuum. To survive micrometeoroid impacts, each ISS module includes layered shielding. Thin outer panels are designed to absorb and disperse the energy of high-speed debris. Connecting 2 pressurized modules in orbit requires extreme precision. Docking mechanisms guide, align, and lock each segment together within tight tolerances measured in millimeters. Once sealed, a new module does not remain passive. It becomes part of the living system of the ISS, sharing power, data, air, and structural load instantly. As more modules were prepared on Earth, the assembly of the International Space Station depended heavily on the space shuttle. Its cargo bay was large enough to carry massive ISS components into orbit. At the same time, Russian rockets launched additional modules and propulsion systems. The ISS was not built by a single launch system, but by multiple vehicles working in coordination. Over time, more than 40 major assembly missions contributed hardware, tools, and structural elements. The ISS grew gradually, expanding with each successful docking. Many of these additions required astronauts to leave the safety of the cabin. Extravehicular activities, or EVAs, became essential to physically assemble the ISS in orbit. Working outside the ISS is slow and deliberate. Thick gloves reduce dexterity, and every movement must be controlled to avoid drifting away from the structure. To position heavy components, the ISS relied on Canadarm2, a robotic arm capable of carefully maneuvering modules into alignment before final attachment. Docking is not a simple collision. Capture mechanisms guide the approaching module, align structural rings, and gradually pull the segments together with controlled force. Once the mechanical connection is secured, astronauts must connect power cables, data lines, and fluid systems. In orbit, integration happens immediately after attachment. Inside the ISS, activation follows a careful sequence. Systems are powered on step-by-step, monitored for pressure stability, electrical continuity, and structural integrity. If a connection fails, there is no workshop nearby. Every bolt, seal, and connector must function as designed, because repair options are limited once in place. Over more than a decade, this process repeated again and again. The ISS did not appear fully formed. It evolved through incremental additions in orbit. What makes the ISS remarkable is not just its size, but the fact that it was assembled while already circling Earth at orbital speed. Construction never paused the motion. As the modules of the International Space Station expanded, a new structural element became essential. Above the pressurized habitats, a massive framework began to grow. This was the integrated truss structure. Stretching more than 100 meters from end to end, the truss acts as the structural backbone of the ISS. It supports critical systems that cannot fit inside the living modules. The truss is not decorative. It distributes electrical power, anchors solar arrays, and holds large radiator panels that regulate temperature across the entire station. Attached to this spine are the solar arrays, which extend outward like enormous wings. Fully deployed, they span roughly 73 meters across the ISS. Together, these arrays generate between 75 and 90 kilowatts of electricity, enough to power a small neighborhood. Every experiment, light, and life support system depends on that steady flow. But sunlight is not constant. When the ISS passes into Earth's shadow, batteries store and release energy to maintain continuous operation throughout each orbit. Electricity generates heat, and in space, heat cannot dissipate through air. Instead, the ISS uses large radiator panels to release excess thermal energy into the vacuum. Without these radiators, onboard electronics would overheat rapidly. Thermal balance is as critical as power generation in maintaining a stable orbital habitat. The truss itself must endure constant expansion and contraction as temperatures shift during each orbit. Its joints and connections are designed to tolerate repeated thermal stress. What began as a framework to hold solar panels became the energy and thermal infrastructure of the ISS. Without the truss spine, the station could not sustain life in orbit. With power and thermal control in place, the International Space Station becomes more than a structure. It becomes a pressurized habitat designed to support human life continuously in orbit. Inside the ISS, air pressure is carefully maintained close to Earth's surface conditions. Sensors constantly monitor cabin atmosphere to detect even minor deviations. Oxygen aboard the ISS is generated through electrolysis. Water molecules are split into hydrogen and oxygen, providing breathable air without constant resupply from Earth. Carbon dioxide produced by the crew does not simply accumulate. Specialized systems remove and filter it, keeping the internal atmosphere balanced and safe. Water is even more carefully managed. The ISS uses a water recovery system capable of recycling more than 90% of onboard water. Moisture from breath, sweat, and even urine is processed, filtered, and purified. In orbit, waste is not discarded. It is converted back into usable resources. Air circulates continuously through ducts and fans, preventing pockets of stagnant atmosphere. In microgravity, convection does not behave the way it does on Earth. Every critical life support component on the ISS includes redundancy. Backup systems stand ready in case a primary unit fails unexpectedly. The station is not designed to prevent all failure. It is engineered so that problems develop gradually, allowing time for diagnosis and correction. Through controlled pressure, recycled water, managed airflow, and continuous monitoring, the International Space Station functions as a closed artificial ecosystem, sustained entirely by engineering. Even with life support functioning, the International Space Station cannot simply remain where it is. The thin upper atmosphere creates constant drag, slowly reducing the station's altitude over time. To counter this gradual descent, the ISS performs periodic reboost maneuvers, attached propulsion modules, or visiting spacecraft fire engines to raise the station's orbit. Maintaining altitude is only part of the challenge. The ISS must also control its orientation, ensuring solar arrays face the sun and radiators remain properly positioned. Large gyroscopic devices known as control moment gyroscopes rotate internally to adjust the station's attitude without using fuel. They allow precise orientation changes in orbit. If the ISS loses proper orientation, power generation and thermal control would quickly be affected. Stability in space is an active process, not a passive condition. From reboost burns to gyroscopic adjustments, the International Space Station is constantly managing its motion. It does not drift aimlessly. It continuously corrects itself to remain operational. The International Space Station was not built by one nation alone. Agencies including NASA, Roscosmos, ESA, JAXA, and CSA contributed modules, technology, and operational control to a shared orbital project. Each partner brought its own engineering standards, electrical systems, and design philosophies. For the ISS to function, these differences had to be integrated into one compatible structure. Power systems from one country connect to laboratory modules from another. Life support hardware operates across components built on different continents, yet functions as a single coordinated system in orbit. In the end, the International Space Station is more than a spacecraft. It is the first large-scale infrastructure assembled beyond Earth, proving that construction is no longer limited to the ground beneath us.